This video is about series, specifically geometric series. So the sum of the first n terms or k terms of a geometric sequence is called a geometric series. So we've already learned about arithmetic series, and now we're going to dive into the geometric series. They have a different formula, of course. And so the formula that we're going to deal with is this one. Again, the formula booklet has two versions, and I like to focus on just one of them, though basically they're the same thing. So it really doesn't matter which one you focus on, they're the same amount of work. So I'll just use the one here that I circled in red. Find the partial sum for the first 20 terms of this series. We're going to just practice using that formula to find the sum of a geometric series, and we're looking for just the first 20 terms. So the formula looks like this. We can talk about what each piece means. The a sub 1, of course, is the first term. R, if you remember, for a geometric sequence is the common ratio. It's what is being multiplied each time to get to the next term. Here, if it's 3, 6, 12, 24, it should be pretty clear that the common ratio is 2. N is, you're trying to find the sum up until what term number, so the 20th term in this case. And then again on the denominator, there's another R down there, so you use the same value for the common ratio. So here we're just going to plug right in. Here is the sequence. The common ratio is 2, so we're going to plug in. First term is 3, 1 minus the common ratio to the 20th power. The common ratio is 2, 20th power, because we're looking for the sum of the first 20 terms. And we calculate it. Now, don't be shocked how big these numbers get, because when a sequence is geometric, if it's multiplied by a number greater than 1, it's getting big very quickly. And then on top of that, you're adding it together to the previous big numbers. So sometimes these sums can be pretty large. Let's think about a sum for which an infinite number of terms is involved, which would be called an infinite series. Can you really get the sum of an infinite number of terms? A sum implies that you've added together a bunch of values and figured out what the total is, but there isn't a total if you have an infinite number of terms. So truthfully, you can't get the sum of an infinite series. In some interesting cases, however, the sum of an infinite sequence actually will approach a finite limit, which is a bit strange. So here's an example so we can appreciate that. Consider the series, and then they show it to us in sigma notation. Here's the formula for it. The geometric sequence, where a bunch of terms are being added together all the way up to the nth term, which just means it never ends. You never stop adding these terms together. If we plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, and try to figure out each term, you get these values over here. These are the first 5 terms, and then we stopped after 5, but it does keep going because it doesn't give us an ending point for this series. If you started to add these together, let's calculate what we would get. So I recommend that you actually do these, take out a calculator and add if you need to. 2 plus 1 plus a half plus 4 plus an 8. And let's see what answer we get. I evaluated this earlier. I got 3.875 when I just added the first 5 terms together. Now it should be clear that each term is getting smaller as you go, right? The next term is going to be 1/16 and then 1 over 32. So they're getting smaller and smaller. So though this number 3.875 is going to keep increasing, it's always going to increase. The next thing I add to it, is going to make it go higher. It's going to increase just by such a tiny amount, and that amount that it increases by gets tinier and tinier. So the sum of the first 10 terms, I calculated it, comes out on a calculator to approximately 3.996. The sum of the first 20 terms would be 3.999996. And it is getting bigger. It's just getting bigger so slowly. And you'll notice if you keep going, adding the first 20 terms, 30 terms, 100 terms, that it's going to get closer and closer to 4, but never actually reach 4. That's called converging. So when the sum approaches a limit like this, we say that the series converges because it's coming toward a specific value. If it doesn't have a limit, like if I was to add 3 plus 6 plus 12 plus 24 and keep going like that, that's just going to get to infinity, right? That's called a series that diverges. Note that a series is only going to converge if the values are getting smaller as you go, right? 2, 1, then a half, then a fourth. So that means that the common ratio is something less than 1. It means that you're multiplying by a half each time, a third each time. So we're ready for the general formula for the sum of an infinite geometric series. So if you are asked to find the sum of an infinite geometric series, and they should only ask if it's a common ratio that's less than 1, here's the formula you can use. It's just the first term divided by 1 minus the common ratio. But note that it's only when the common ratio is less than 1. What if r was greater than 1? Sorry for that little blip. So what if the common ratio is greater than 1? Then there isn't a sum because it would be a divergent series. So you probably won't be asked that, but if it ever happens, just note there is no sum to this infinite series because it diverges, gets bigger and bigger. So here's an example. Find the sum of the infinite geometric series. First term is 0.6, which is 6/10. Next term is 0.06, right, 6/100. So it's an infinite geometric series. The terms are getting smaller. First term is 0.6. Common ratio here is 0.1. Remember, if you ever can't determine the common ratio, you can divide any term by the term that came before it and get the common ratio. And so then we're just going to plug right into this formula. First term on top, over 1 minus the common ratio, and it comes out to whatever the infinite geometric series converges to. So this one converges to 2/3. Here is another example. Okay, sorry for that little blip as well. So here we have a final example of a geometric series in application. The ball has elasticity such that it bounces up 80% of its previous height. So when it hits the ground, it then bounces back up to 80% of its previous height. We're going to find the total vertical distance traveled down and up by this ball if the initial drop height is 3 meters. The initial altitude is 3 meters. So I drew a little visual of the ball bouncing. You can picture it being dropped from the top of the first red curve, and the vertical distances are indicated by the black dotted lines. So the first vertical distance traveled is the first dotted line here. But then each subsequent black dotted line, the ball travels up that distance and down that distance. So this can get a little bit tricky when you're trying to apply the geometric sequence formula or a geometric series formula. So it is an infinite geometric series because it never says that the ball stops. So we have to assume that this 80% pattern is going to continue happening. Notice that I'm saying that the first term is 2.4 rather than 3, and that's because I'm going to not include the one that I have the arrow pointed at now. I'm going to not include that vertical distance, and I'm going to just add that on at the end. I'm going to start this sequence as if 2.4 is the first vertical height. That's because 3 times 80%, or times 0.8, is going to be that 2.4 meters. So that means our first vertical distance that we're counting in our geometric series is going to be 2.4. And then every other one after that is going to be applied the common ratio of 0.8. So I can use the formula for getting the sum of a geometric infinite series by using 2.4 as the initial first term and then 1 minus the common ratio, and that comes out to 12. So 12 is basically each of the rest of the dotted lines other than the first one when they all get added together. Now, like I said, because the ball is going up and down, you have to remember to multiply that 12 by 2 because it's an up and a down for those distances traveled. And then I'm adding the 3 from the first initial drop. And so the total distance traveled is 27 meters for this ball as it's dropped. So that's a bit of a tricky application. We can practice that more if you're worried about it coming up on an exam. And that is all.